Okay, the remainder theorem. Use synthetic division. So again, we're just going to practice the synthetic division we started the other day, right? Because you need to get that algorithm down. So $2 word for the day, algorithm, right? What's an algorithm? Just a series of steps to solve a problem. You often hear about it in computer science. There's an algorithm, right? There's a series of steps. And really, that's what you need to do. In Betty Crocker, it's the make it cake mix simple, right? Come up with a series of steps that you say, here's how you're going to do a transformation problem, right? First of all, I'm going to rewrite it in the form, like -2 bracket y minus 3, right? And then from that, I'm going to make the description, right? I could describe everything, and then from there, depending on what I'm doing, if I'm doing a mapping, then I can translate the point x, y, right? Or the specific point, 2, 3, becomes blah, 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 one step at a time. So the algorithm for synthetic division. So you write down x minus 2. Now in some places you won't see it. They'll just put down the -2. They won't write. We write x minus 2, okay? Because it's the divisor. The polynomial, we don't put in the x cubed, x squared, something, because really it's only the numbers that matter. So if I don't see this, but I see this, then I would say, okay, that's the constant x term x squared x cubed. So I can read it as, say, 3x cubed plus 5x squared plus 6x minus 4. Okay. Now we need a placeholder for every thing below cubed, right? Now in this case they exist, so we don't have to worry about it. But if it didn't exist, we'd have to put a 0 in there. Okay. Anyway, this exists, and we did one yesterday. So the first step is bring down the 3s. Right? And if you think about long division, what would we do? We put a 3 in front, 3x squared in front, we multiply by 3, and then so you bring down the 3, right? You bring down numbers. Then we go -2 times 3 is -6. 5 minus -6. I know you've all thought about how to do this, arithmetic. So 5 minus -6 is 11. -2 times 11. 6 minus -22. Positive 28. -2 times 28. You can work on these skills if you're doing 31 because you don't know how calculators. -56. -4 minus -56. 52. Okay. So what's the remainder? 52. The quotient is, so if I'm reading the quotient, I say constant term square, or x term x, so it's 3x squared plus 11x plus 28. Okay, we don't need that here. That's not what we're interested in. Determine f of 2. Okay, well there's f of x, so f of 2 is equal to, all we do is substitute wherever we see an x, we're going to write it 2. So 3 times 2 cubed plus 5 times 2 squared plus 6 times 2 minus 4. And we're just going to evaluate that, right? Determine f of 2, just work it out. So 2 cubed is 8 times 3 is 24. 2 squared is 4 times 5 is 20. 6 times 2 is 12 minus 4. Okay, 24 plus 20 is 44. And then the 2 is 46. 56 minus 4 is equal to 52. Coincidence? Well, first, is f of 2 equal to remainder from part A? Yes. This is only a coincidence, you say, or not. Maybe you didn't say that. Let's check in with another example, right? So right now we can start to form a hypothesis, right? I mean, what type of reasoning are we doing? Yeah, it's like in 29 font, right? There's some reasoning in there. It's inductive reasoning, right? So all we do is we're trying stuff out, and we're going to see is there a pattern. What's going on here? Right now we know that, hey, so if I divide by, okay, let's try this one. If I divide by x plus 3, we're going to get a certain remainder. And then what happens if we determine g of -3? All right, 4x cubed, no x squared. So I need a 0 there, right? I need a placeholder. So that looking at this, I could say the constant term, the constant term, the x term, the x squared term, and an x cubed term. right? Or you can just count them, and the degree of this is going to be 1 less than the number of terms you count, because there has to be a constant, right? So it's like 1, 2, 3, 4. Okay, I've got a term of 0, 1, 2, and 3. Okay, bring down the 4. Okay, you try it. Come up with the remainder. But the short underneath, same colors, but it's from Rome. So. I advertised the trip today. I get the paper out. Hey, we're going to trip on Rome. Sucks to be you because it's long. Unless you signed up. It's good. Okay, now determine g of -3. And will we be surprised if we see what are we going to do, like 30 and then subtract 108? Negative 123. Oh, wait, sorry. Is the remainder the same? Yes. Are you convinced now? Yeah, you shouldn't be, right? Really, 2 examples. But, that was a really weird number, right? Like negative 130. So it's probably, at this point, you should be saying, not necessarily a coincidence, but can you prove that? We're not going to prove that, okay? But it can be proved, okay? So are you convinced now? Yeah, maybe. Yes. Based on your result, complete the following. So this is the remainder theorem, right? And we don't prove theorems usually, right? We just use them. Okay. So we looked at it and we said, hey, that's interesting, and it seems to be a thing. So when a polynomial f of x is divided by x minus a, the remainder is equal to what? Well, it's not equal to a, so we have two examples. So when I divided by x minus 2, the remainder was equal to f of 2. When I divided by x plus 3, the remainder was the same as g of -3. So when I divide by x minus a, the remainder is equal to f of a, where a is the number following a minus sign, right? In other words, the remainder when f of x is divided by x minus a can be determined by evaluating the polynomial at x is equal to a. Likewise, f of a can be determined by finding the remainder when f of x is divided by x minus a. Yeah. Okay, interesting. So that's the remainder theorem, right? It says the remainder that you're going to get if you divide by x minus a is equal to f of a. You don't have to do the long division. You can simply evaluate f of a. Halfway. Write a conclusion giving the following statements. When g of x was divided by x plus 5, the remainder was -12. Therefore, what can we say? G of -5 is equal to -12. Okay, so if you tell me, hey, I did a division by x plus 5, then you say, oh, well, then the remainder you get is going to be the same as if you evaluated g of negative 5. If I tell you that p of 6 is equal to negative 17, then you could say, what can you say? Say the remainder when p of x is divided by x minus 6 is negative 17. Yep. Yep. And that's what they said. I just didn't write it correct, but thank you. We need a good record of this, right? Okay, so we're just kind of saying it works both ways, right? If you know you divided by something and got the remainder, then you know that if you evaluate the function at x minus a, so with x plus 5, then it's negative 5. Or if you know that a function evaluates to something, then you can say, oh, that's the remainder that you'd get if you divided by x minus whatever the something. Question? No, good. Determine the remainder when f of x equals x cubed plus 5x minus blah, 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 is divided by x plus 1 by using synthetic division. Okay, more practice. So x plus 1. Got all my numbers, so 1x cubed, negative 4x squared, 5x minus 1. Okay, if you like, you could throw a little line in there because the remainder will be to the right of that line. Synthetic division, bring down the first number, multiply, subtract, multiply, subtract. So negative 4 minus 1, negative 5, negative 5, positive 10, positive 10, negative 11. Remainder theorem says, what do I do for remainder theorem? I'm going to evaluate f of what? Negative 1. Okay, it says determine, so for us, it means show work. So you want to show what I'm doing. Look, I'm evaluating f of negative 1, and look, here I am putting negative 1 in wherever there's an x, and I'm doing the stuff to it. Okay, and now, that's a negative 1. This will be minus 4, minus 5, minus 1, and not surprisingly, right? It's also a way that you could check things over, right? If I do the division, I get a number, and I want to say, is that right? I can evaluate the function at that, right? And you can use your calculator for that, obviously. So, where do we go from here, right? We've got this remainder theorem. Now what? Well, we've got a couple of questions. When p of x, which is defined by x cubed plus kx squared plus 2x plus 9, is divided by x minus 1, the remainder is 7. Determine the remainder when that same polynomial is divided by x plus 2. So what do you need to figure out first? K. So how are we going to figure out k? So when I say, when p of x, so forget that p of x exists as a thing. If I say, hey, p of x is divided by x minus 1, the remainder is 7, then you can immediately say that means that p of 1 is equal to 7. So let's say it. P of 1 is equal to 7. Okay. So it's like asking you something where you know you have to find the x-intercept, so just say, hey, I need to find the x-intercept. Or I need to find, this x cubed plus blah, blah is equal to 0, right? Like that's what I need to find. So communicate that in your solution, right? So this is what I'm telling you. All right, I know p of 1 is 7. But what's p of 1 also? So that means that 7 is equal to 1 cubed plus k times 1 squared plus 2 times 1 plus 9. Right? So p of 1 is equal to this, But p of 1 is 7, so 7 is equal to the polynomial evaluated at an x value of 1. Which means now we can solve for k. So, what's k? All right, assuming any of this is correct, it shouldn't be hard to work out k. What's k? Negative 5. Okay, so now we think, well, we hope k is negative 5. You know, if it's not and you work out the rest of the question, how many marks would you lose on this if you had k wrong? Like a half a mark, right? Because we're interested in process, right? It's a procedure. Are you able to go through the steps correctly? Are you able to communicate them, right? So that's pretty obvious. The fact that you make an arithmetic error, that shouldn't count that much against you. It's not like you're building a bridge that's going to fall down. Later on you'll do that. Well, you may not build bridges that fall down, but you know, later on if you're building bridges, there are many other people checking the work, right, to make sure that the bridge doesn't fall down. So here we're interested in, can you go through the process? Okay, so that's the first part. Now what? Well, we know that p of x is equal to, so we're supposed to determine the remainder when this is divided by x plus 2. How do we do that? We want to work out p of negative 2. Okay, what's that equal to? Well, negative 2 quantity cubed minus 5, because we know k, right? K is negative 5. So minus 5 times x squared, so negative 2 squared, plus 2 times negative 2 plus 9. Okay, everybody good with that? So the first part of the question gave us the information that allowed us to determine k, and the second part of the question is just, okay, now use the remainder theorem. And hopefully, so minus 20. What's that? What is that? 23? Minus 23? Okay, so negative 23. If you wanted to, you could say the remainder when p of x is divided by x plus 2 is negative 23. Right? It's always nice to somehow set your answer apart, because what's the first thing I look at when I'm marking, right? Look at the answer. Is the answer right? Good. Is there work supporting the answer? You know, is this a jumbled mess? Sometimes it's a jumbled mess, hard to figure out what's going on, right? So remember, anytime you're getting an answer, it's not about the answer. It's about communicating the solution, right? It's about showing how this came to be. That's what I'm looking for if it's not a multiple choice numeric response. How did this come to be? By the way, if it's multiple choice numeric response, on that sheet, please show your solution. That's for you, right? So you look back later and it's like, I got this wrong. Why did I get this wrong? Like, if there's nothing on your sheet and it's wrong, what do we know? I know this much. When you try and work it out again, you will not get the same wrong answer you got the first time, right? You can't duplicate your mistake unless it's there for us to see, right? You'll actually end up getting the right answer, and then you'll, why did I choose this? And that's, why did you choose this? I don't know. So show your work, right? And if there's no work there, that could just be the key to everybody that, yeah, I didn't know what I was doing, so I guessed, right? Because you should fill in something. But show your work. Because that's what we could sit down in wise time and look at and say, oh, that should be a plus. That should be a plus. Right? And what's the important thing to figure out when you get an answer wrong? Was it an arithmetic error, or do I not understand what I'm doing, right? Like, oh, I threw a half in and it should have been a 2. When g of x, which is equal to kx cubed plus px squared minus x plus 3 is divided by x minus 1, the remainder is 4. And when g of x is divided by x minus 2, the remainder is 21. Determine the values of k and p. You have two unknowns, so what word pops into mind when you have two unknowns? System of equations, right? So you should be thinking, so you say, I got two unknowns. Not only do you have two unknowns, you also have two pieces of information, right? The remainder when it's divided by this, the remainder when it's divided by that. Those two pieces of information are going to lead you to two equations in two unknowns, the system. Okay. Now, if that doesn't immediately pop to mind, then at least you could start with this. When g of x, the remainder is 4, so what do I know? G of 1 is equal to, and g of 1 is k. So we know g of 1 is 4, but we also know g of 1 is k times 1 cubed, etc. So what do we get? So forget the g of 1 here. Let's do that. So we got 4 is equal to k plus p plus 2. So we got minus 1 plus 3. So we get, what's k plus p equal to? 2. Now I just like to rewrite it so that my stuff is on the left-hand side. I write the unknowns because I like systems when it's like x plus y equals. Okay, what else do we know? G of 2 is equal to?
21.
Okay, I'm going to say leads to because I just don't like stringing equals along a line. So g of 2 we know is 21, which is equal to k times 2 cubed plus p minus 2 plus 3. Okay, that's 21. So what can I say about 8k plus 4p? Equals 20.
Divide that by 4 and substitute it.
So I have many ways I can solve this, right? So Jesse said, divide through by 4, just get like 2k plus p is equal to 5, and then do substitution. You could just say p is equal to 2 minus k, substitute in. You could say k is equal to 2 minus p, substitute in. You can multiply this by 8, write it underneath, do subtraction. Actually, I would write that underneath and end up with a positive thing. So solve the system. There you go. Pick a method. Doesn't matter, right? Substitution, elimination, whatever you like. Just solve the system. Get the values of k and p.
Or is that 80k plus 4?
Mr. Yano,
Yeah.
your 8Ks all kind of look like 81 less than symbol. Just kind of
Suck it up, princess. Yeah, I know. That's why I always say stuff. Yeah. I prefer. I should be using a scripted k, right? That's why I avoid t's
Yeah.
and x's, right? So if I'm gonna do a t, then I should do t. And an x, don't do this because now it looks like that could be a multiply. So k, let's script the k. Yeah, whatever.
It's close enough.
It's just no satisfying. But why didn't they use x and y? I can write pretty good x's and y's. K is 3, p is negative 1, that's just sort of obvious. Although, really, if we want to show that, then we go over here and we say k plus p is equal to 2, 3 plus p is equal to 2. Okay, so there's my answer. Put a little box around that so I can identify. Okay, so on your paper you do that, I'm looking and say, oh, there's the right answer, and I look at the work and I say, yeah, that looks like it would lead to the answer, which in 20-1 test the other day was not actually the case. Like, here's the answer, and then here's some stuff which, if you don't actually look at it closely, you might think led to the answer. No. Sorry, that didn't work. It's like, because the answer was easy to figure out, right? But the work to justify that wasn't quite there in some cases. Okay?